Welcome back. We're going to now talk a little bit about chemistry that you have seen in the past as it pertains to aldehydes and ketones. So the first reaction I want to revisit is the oxidation of alcohols into carbonyls. Specifically, if you start with a primary alcohol, you could treat that with pyridinium chlorochromate, or PCC for short, in the absence of water, and it will give you the corresponding aldehyde. Alternatively, you could start with a secondary alcohol, also oxidize it with PCC in the absence of water, and that will yield the corresponding ketone. And you may also recall that for the aldehyde and ketone components, you could always treat them with a hydride reagent like sodium borohydride, which is mild, or even a strong reagent like lithium aluminum hydride to fully reduce the aldehyde or ketone back to the corresponding alcohol. After that, another reaction that allows you to prepare ketones and aldehydes is ozonolysis of alkenes. In particular, you do need to use zinc or dimethyl sulfide to complete the reaction. But in essence, all you're doing is breaking apart the carbon-carbon double bond and replacing that double bond with a carbon-oxygen double bond for the two smaller fragments. Another reaction that also yields carbonyl compounds is the reaction with mercury sulfate in this case. You could also use mercury acetate. It works the same way. And mercury, being a big ion, tends to favor the position of the alkyne that is less hindered. And so that will mean that the mercury will tend to hang around the terminal carbon of this alkyne. And then that allows for water, which is pretty much you're doing this in aqueous solution, to have those components dissolve. The water attacks the more hindered carbon, which ultimately allows you to prepare a ketone with a molecule, right? And then sodium borohydride is there just to simply reduce the mercury back to elemental mercury and get it out of the way. The complementary reaction to this is the borohydration oxidation, in which you first react your alkyne with borane, and you follow that up by removal of boron using basic peroxide. This, in essence, inserts an oxygen on the least hindered position of the alkyne, which ultimately, after tautomerization, will yield an aldehyde. So these are all the various routes that you have seen in the past. Now, other things that you've also seen in the past, which I should probably remind you right now, is a spectroscopy, right? In particular, we're going to look at the infrared spectroscopy first. Basically, you may recall that when it comes down to IR, there is a couple sections that I want you to remember in particular. For instance, the mark at 3000 tells you whether you have CH bonds that are present on sp2, sp, or sp3 hybridized carbons. If you have peaks that show up below 3000, here to the right of it, you have CH bonds to sp3 carbons. If you have peaks that are a little above it, to the left of it, you have CH peaks that are on sp2 carbons. And if you have a peak that shows up roughly at 3300, that's your CH peak to an sp carbon, which basically will tell you that you probably have an alkyne present in this particular molecule. Now, another thing to point out, right, is that if you do have an alkyne, you do have to have triple bond signatures present in the molecule, and typically your carbon-carbon triple bonds, your carbon-nitrogen triple bonds are going to show up, in this region of like 2000 to 2300. After that, between 16 and 1800 is where you're going to find your carbonyl peaks, and slightly below that, from 15 to 1600 is where your carbon-carbon double bonds tend to show up. So these are like the main regions that you have to be aware of when it comes down to the infrared spectrum. And needless to say, for the aldehydes and ketones, you're going to be ultimately concerned with looking for peaks showing up between the 16 to 18 inverse centimeter region of the spectrum. Now, the bending modes sometimes are helpful, but I personally don't pay too much attention to them because the fingerprint range tends to be a little bit more variant in terms of what it shows up. So let's get a little bit more specific. Let's look at ketones to see what exactly it is that we have or we expect to see. Now, ketone basically has the carbonyl peak, and aside from that, there's not much else going on. So really, the only peak that we expect to see, if a ketone is all you have, is a strong carbonyl peak at about 1720 inverse centimeters. That's a very typical position for which ketones tend to fall, but you do have to have a pretty strong signal. So it cannot be like mid-range, kind of weak. It's got to be kind of strong, almost touching the x-axis in the spectrum. And you can kind of see the same thing happening, as you increase the size of the ketone. You're still within that 1720, range. Um, if we make this a little bit more symmetrical, same idea, you're still within that vicinity. And then now this part is kind of interesting because with the ring systems, it's kind of a similar story. Now the six-member ring, which has perfect, 109.5 degrees of bond angles, for the inside of the ring, you perfect tetrahedral, bond angles. You tend to see values similar as to what the ones we saw for the non-cyclic counterparts. But when the ring becomes a little bit smaller and the bond angle inside of the ring becomes also more acute, you start seeing that the carbonyl signature peak starts going up in value. And so right now we went up by about 20 inverse centimeters. And then if we decrease the ring even lower to a four-member ring, we see this bumping up by another 40 inverse centimeters. This ultimately has to do with the hybridization um, of the carbonyl bonds in relation to the bond angle of the ring. If you are curious about that, I recommend that you take a look at some of the earlier videos on IR spectroscopy that I posted. All right, but let's take a look at aldehydes now. Now, aldehydes will also have this carbonyl peak that has to be strong, right? And it falls roughly in the same vicinity, 1720s. But in addition to that, there is this double molar peak that shows up between 28 and 2600. And this is a key signature peak for the aldehyde CH bonds. So if you do claim to have an aldehyde, you better have this molar peak along with the carbonyl peak present in your spectrum. If you don't, then you probably don't have an aldehyde. But you can kind of see that, if we go to a much complex molecule right here with a bunch of substituents, you still have that molar there present on the 26 to 2800 region. You do have your strong carbonyl peak around 1720. And even for the carbaldehyde molecule right here, so cyclohexane carbaldehyde, you still have the double molar, although this one's a little bit harder to see because the leftmost peak is a little bit buried on the major portion of the CH bond of your typical sp3 hybridized carbons, but you still kind of see the molar in there along with the 1720 peak. So those are kind of like the things that you want to be on the lookout for. Now, aside from that, your NMR peaks and your carbon NMR peaks are also important to keep in mind. Your aldehydes are going to show up between 10 and 11 ppm in the proton NMR spectrum. And in the carbon NMR, they tend to show up the farthest downfield, like pretty much in the 200 ppm region. So if you see a peak up there, you're probably looking at an aldehyde. And then for the ketones, the proton NMR is going to show you only the CH peak, right? That comes after, you know, the carbonyl. The carbonyl doesn't have any hydrogens on it, so you're looking at the neighbor. And they tend to fall around 2 ppm just because of the proximity to the oxygen, the carbon-oxygen double bond, and the level of induction that happens there. And for that same carbon, the adjacent carbon, you tend to see them, falling between 40 and 60 ppm. The carbonyl carbon itself is also going to fall, close to 200 ppm. So those are kind of some of the things you want to keep in mind for your proton and carbon NMRs, as well as the infrared spectrum. All right, so with all of that said, in the next video, we are going to then investigate the newer reactions, the newer chemistry that we've been basically keeping under wraps up until this point. So the new chemistry basically starts on the next video, and I'll catch you there. Bye-bye.